Okay, welcome back. So in the last lecture, we derived the equations for optical flow. In this lecture, we're going to study them in greater depth and show what use they provide us for computer vision or, in fact, any biological vision system. So let me begin by reminding you of the equations which we derived last time. These were shown last time. And the way to understand these is that there is a translational component and a rotation component. I want to make one bit of notation clear. These are vector equations, so I've kind of written them out in a compact way, but these are two vector equations which really consist of the two scalar equations. So in fact, if I take this matrix vector multiplication and I carry it out, I will get two rows. And similarly, I will get two rows here, and these are also two rows. So if we consider the first row, that corresponds to the equation for x dot, and the bottom row corresponds to the equation for y dot. So just to make clear that I have expressed in a compact way using vector notation what really are two separate equations, one for the x component of the optical flow and one for the y component of the optical flow. So let's get going, and first we'll concern ourselves with the translational component, all this red stuff here. So what's the optical flow for pure translation? If the motion is purely translation, we can ignore the rotational component because the omegas are zero. Omega x, omega y, omega z are zero, and then the flow field is given by these two expressions. This is just from the previous slide. Just substitute omega equals 0. Okay, I want to get some intuition about this. How am I going to do this? Because just leaving this as formulas doesn't give us proper understanding. So we are going to gain intuition by considering this special case of translation along the optical axis. So what's this special case? So there's translation, but the translation is along the z-axis. So imagine that there's a camera moving, but its movement is just movement along the z-axis. There's no movement along x and y, there is no rotation. So imagine that you're just looking straight ahead and you're walking in the direction in which you're looking. Well, this is what most of us should do most of the time. What does the flow field become? We can start with the expressions here and we can substitute that t sub x and t sub y are 0. So we get the expressions shown here for the x component of the optical flow u and for the y component of the optical flow. And let me do my standard trick of writing these two scalar equations as one vector equation, and that's what I do here. So this uv transpose really means little u, little v as a vector, and this xy transposed is x and y as a vector. So these are column vectors, and here these are row vectors which have been transposed with the letter t. Okay. So we get a fairly simple looking expression. So the optical flow vector is proportional to the position vector xy, and the proportionality factor is tz upon z. Let's see if we can plot this out. Okay, so I repeat. UV is UV, the optical flow vector. The optical flow vector here, this is the position vector, and the proportionality constant is Tz upon Z. This diagram shows what the optical flow field looks like in this case. So first of all, what happens when we are at the origin? So the origin here. So at the origin, x equals 0, y equals 0. So the optical flow must be 0. UV must be 0, 0 at the origin. So that's shown here by this is the origin of the image plane, and at the origin what we should have is that the optical flow vectors are of length 0. The optical flow vector is a scalar multiple of the position vector. This has a very simple meaning. This means that if I have a point xy, so there is essentially the position vector which is drawn here in blue, the optical flow vector at the location xy is in the same direction, scaled by some factor, and that factor is tz upon z, and but it points in the direction of the position vector xy. So this means that all the optical flow, so at this location here xy, the position vector is going to be like this. So the optical flow vector is in a scaled copy of that. The scaling factor being given by tz upon z. So the optical flow pattern has this very beautiful starburst-like pattern to it. All these vectors appear to be streaming out. Actually, they are streaming out when we are approaching an object. So imagine that I'm driving and I'm driving headlong towards a wall. So the wall is ahead of me at 10 meters. Its z is constant at 10 meters and I'm driving towards it. Well, I hope I'll brake at some point, but before I do, I see this optical flow pattern, which is all these arrows streaming out. Okay, what will happen if I was reversing the car, if I was driving back? Well, at that point, what will happen is that the sign of tz will flip. So all these vectors, instead of pointing outwards, would be pointing inwards. So when I'm driving towards the wall, the optical flow is streaming outwards. When I'm driving away from a wall, I'm reversing from the wall, the optical flow vectors will be streaming inwards. And this proportionality factor is tz upon z. So that's a very nice property of the optical flow field. The lengths of these vectors are proportional to tz upon z, and let's try to get a better understanding of that. Okay, there is one little problem which confronts us in our analysis of the optical flow field corresponding to pure translation. So this property is called the scale factor ambiguity. So imagine that I took the world and I made the world k times bigger, and I made my movement k times faster. So I made the world z becomes kz. So imagine that everything in the world is twice as big and I move twice as fast. What will happen to the optical flow? Since tz upon z, that ratio is not going to be changed, the optical flow field will be exactly the same. So this is something we have known how to exploit for quite some time. People in the movie making business can make these tiny toy sets with a tiny Godzilla and a tiny building, and then they can move the camera only a little bit, but the optical flow may be the same as if you had a fast moving camera and a larger world. So the optical flow vector is unchanged. This tells us that we have no hope of recovering the absolute speed tz or the absolute depth z. So in a sense, this is bad news, because our goal was to use the optical flow field to tell us something about depth in the scene, and there is no way out. There is no way to recover absolute depth in meters and absolute speed in meters per second. But there is one little important thing we can do. In fact, the most important thing with respect to navigation. I want you to tell me what z upon tz is. So the units of z is a distance in meters. T sub z is a speed in meters per second. Okay, what does this ratio tell me? This ratio is, so imagine that there's a wall at a distance of z and I'm going at speed t sub z directly towards it. Well, z upon tz is the time to collision. So you can work out that the units of this are in seconds. So z upon tz is in how many seconds am I going to collide with the wall. So, and here the scale factor ambiguity doesn't come into play, because it could be that the z is in kilometers and t sub z is in kilometers per second, or z is in meters and tz is in meters per second. It's the ratio that matters. If you're moving faster but the world is is bigger, it will take you the same time to collision or time to contact. So the important point is that this proportionality factor tells us about the time to collision. And now here is a bit of advice. If you're driving towards a wall, just keep the time to contact positive. That will keep you out of trouble. So in fact, this advice seems to be followed by insects and birds and so on and so forth. There have been quite a few experiments done by biologists which demonstrate that time to contact is a very valuable variable which is in fact used. So what you do is you can control essentially braking behavior by making tau decrease as appropriate. Okay, I'm not going to get into the details of those studies, but the beautiful result is that from the optical flow field we can determine time to contact, which is in fact the variable we want to use for controlling our braking behavior so as to avoid colliding with obstacles. Let me now turn to the case of general translation. I did now the baby case corresponding to translation along the optical axis. What happens when we consider a general translation? So we have a t sub x, a t sub y, and a t sub z. So to work this out, let's start with figuring out when is the optical flow 0, 0. So in the previous case, the optical flow was 0 at the origin. In this case, the optical flow will be 0 at the following points. Let's figure out when the x component of optical flow is 0. Minus t sub x plus x t sub z equals 0. So therefore, x should be equal to t sub x upon t sub z. Minus t sub y plus y t sub z should be 0, which implies that y equals t sub y upon t sub z. What this tells me is, if I consider the point tx upon tz, comma, t sub y upon t sub z, at this location, the optical flow uv is 0, 0. So this point tx upon tz, ty upon tz is the moral equivalent of the origin in the previous case. We will call this point the focus of expansion. And let me do a little calculation to show why this term is appropriate. What we should do is, let's take the optical flow field, but let's do a change of coordinates. So imagine that instead of taking the standard origin, which is 0, 0, let's consider a new origin, and let's make the new origin at the point tx upon tz and ty upon 2z. So therefore, we have changed coordinates from x to x prime and y to y prime by just a simple shift. So in this diagram, I have xy, which is the standard coordinate system, and then I have a new coordinate system for x prime, y prime. So the optical flow field in the new coordinate system. So let's go back to the expression here. So here we have the optical flow field in the xy coordinate system, and instead we want to write it out in the x prime, y prime coordinate system. And we'll do a change of origin from xy to x prime, y prime, and rewrite these expressions in the x prime, y prime coordinate system. Again, I leave you to work this out, but if you do that, you're going to get an expression which now looks very simple. It is that uv in the x prime, y prime coordinate system has the simple tz upon z x prime, y prime. So we again get this scale factor relationship that we saw in the easy case, but now we have to refer everything to a new coordinate system located at tx upon tz, comma, ty upon tz. So we will call this tx upon tz t comma ty upon tz to be the FOE. FOE is how we abbreviate it, but this corresponds to the focus of expansion. And why do we use this term? Recall that in the case of translation along the z-axis, the optical flow vectors appeared to stream outwards from the origin, and we could call the origin the focus of expansion, because that's the point from which all these vectors appear to be streaming outwards. Here, these vectors will be streaming out with respect to the point tx upon tz, comma ty upon tz. So these are the coordinates of the focus of expansion. So in a sense, if I have an optical flow field, all I have to do is look, and it corresponds to pure translation. There will be a point at which the flow field is zero, at which the flow is zero, and all the vectors will appear to be streaming out from there. That is the focus of expansion. And the focus of expansion directly tells me about the direction of translation, because the coordinates of the focus of expansion give me tx upon tz, ty upon tz. So this basically is information about the translation vector t. It does not have absolute information about the magnitude of tx, comma ty, comma tz, but we can never hope to get that because of the scale factor ambiguity. All we can hope to do is to recover the direction of translation, and the location of the focus of expansion gives us exactly that. So now we have understood the case of translation, which is beautiful, because the case of translation shows us that we cannot recover the absolute velocity of translation. We can recover the time to collision. We can recover the direction of translation. Of course, in the general case, we don't just have translation, we also have rotation. So this rotation component is described here. This is the rotation component. So I could spend a few slides on trying to understand the rotation component. So imagine that there is no translation at all, and the camera is just rotating. Well, I can do that, but there is really not that much inside there. It's kind of boring. If you rotate the camera, well, the world will appear to rotate. But it tells you nothing whatsoever about the distance of objects in the world, because if you see this expression, z does not figure. It only depends on image plane coordinates, little x, little y, which we know, and the omega vector, omega x, omega y, omega z. So therefore the flow field, the rotational flow field, will tell us how we are rotating. So it will tell us information about omega. It won't tell us anything about the c. So here is the straightforward story. Now, if we have translation and rotation going on at the same time, then algorithmically we do have a challenge of trying to separate the translational and rotational components. A number of algorithms have been developed for that, but I won't get into the details of that. What I'm going to do now is to just show you some pictures of the flow fields and how they reveal information about the scene. So here's an example. This is what the flow field looks like if I'm translating along the z-axis towards a wall edge. So there is a focus of expansion, which is at the origin. All these vectors are streaming out because I'm driving towards the wall. And that's about it. There's a focus of expansion is at the origin. And we have information in the lengths of these vectors about the time to contact. Okay, this is what the optical flow looks like for points on a road. So here I'm imagining that I'm driving on a road so the upper half of the image plane is the sky, the lower half of the image plane is the ground. There is a horizon here, if you like. The optical flow vectors are, here the z varies. So since the z varies, these are nearer points, and these are points essentially at infinity. These are far points. So recall that in the optical flow translational component, there is a 1 upon z factor. So when z is at infinity, the optical flow has to be 0. And when points are nearer, the optical flow is larger. So this is what the flow looks like on the road. And you can have a chance to experience this, particularly when you're driving after it has rained. So the water drops on the road surface, they enable you to sense the optical flow more vividly, and you will exactly perceive these vectors. Another way to think about this is that the focus of expansion is really the vanishing point corresponding to the vector of translation. Because when I'm driving, every point in the road is moving with velocity minus t. So these are all vectors, and these are all parallel to each other. So there must be a vanishing point of this family of parallel lines. And what is that vanishing point? That is the focus of expansion. So the focus of expansion is really just the vanishing point that we studied earlier in disguise. Okay, this is a truly boring case. So imagine that I'm translating along the x-axis in front of a wall. So I'm just moving the camera to the side. The wall is at some fixed distance. Nothing changes. The optical flow is as boring as you get. Okay, here is the optical flow field when you keep rotating the camera about its axis. So you get this rotational pattern. It tells us what you are doing to the camera. It doesn't tell us anything about whether the wall is near or far, or whether we are going to collide with it in 5 seconds or 5,000 seconds. Here's an interesting case. This is rotating about the y-axis, which, given the coordinate system we like to use in cameras, is vertical. So when you're rotating about the y-axis, this is what the flow field will look like. Let me conclude by talking about the importance of optical flow. The big idea that I want you to take away from these last few lectures is that suppose an animal or a robot could analyze its video signal and measure the optical flow field. It could use this data to compute depth and ego motion. Depth z of xy, and ego motion, which is the translational and rotational velocity. You may not get exactly the z or exactly the t. You may get some ratios of that, but that is good enough for controlling your movement. There's a fair amount of evidence from perceptual and neuroscience studies that animals in fact have both the ability to measure optical flow. So this is required. So there is some neural hardware that is needed to measure optical flow given the image as a function of time, given the video data. And that given that we have computed the optical flow, given that we have measured the optical flow, can we use it to control our movement, avoid obstacles, etc. And flies use it, diving birds use it, many animals use it, and we could use it for robots. There is in this whole enterprise this requirement that we must have a way of computing the optical flow field given video signal. And I have not told you how to do that. This requires work. It's not trivial, because essentially to measure the optical flow, we need a way to know what are corresponding points over time. So if there is a location xy in one time frame, and then I say that this point has moved to x plus delta x comma y plus delta y, I need a way to say that there is a notion of corresponding points over time. And this requires an algorithm and some computation. We are going to study that later. For now, I've just shown you how, if we could measure the optical flow field, we could use it for a number of useful applications. Thank you.